In this lecture, we will see in detail about the translational operator, how it is used to make Bayesian transform. And as one of the application, we are going to see the Bloch theorem. This comes under symmetries in quantum mechanics. I am going to give series of lectures in quantum symmetries in quantum mechanics. This is part 1. First, we will see the translational operator. Uh, T cat, which is a function of A, is a translational operator. When it act on psi of h, that is wave function psi, then it will shift the wave function by an amount A. That is, this will become psi will become psi x minus A. This is somewhat shifting. It will shift the wave function position from origin to right or left. Now you use the Taylor series to expand this psi x minus a, which is equal to summation over n equal to 0 to infinite 1 over n factorial minus a power n tn, that is a derivative. First order, second order, third order, it will go like this. So Tn over Tx power n, psi of x. Now what I am going to do is, in the differential operator, I will multiply and divide by I h cross. Now what will happen? This h cross I uh, t by tx is nothing but our momentum operator. So here I already have one I and h cross. So this will become I over h cross, the momentum operator pk p cat whole power n psi of x. Uh, Now this equation can be written as when the t cat act on the wave function psi, you will get this thing. Now I am reducing it further. I am bringing this term inside this bracket, minus a also inside this bracket. So this will become summation over 0 to infinite 1 over n factorial minus I a over h cross p cat power whole thing power n psi of x. Now we got that the translation operator T act on psi of x. We will get summation over n equal to 0 to infinite 1 over n factorial minus ia over h cross p cat whole power n psi of x. If you look into the summation term carefully, this is nothing but exponential I a over h cross p cat. So now your translational operator t is nothing but this exponential minus I a over h cross p cat. Here the momentum is the generator of translation. That means using a momentum operator, you can make the translation. So translation will be obtained by using the momentum operator. That is Bayesian translation will be obtained using the momentum operator. That is important point. Now, if you take T inverse, So this inverse of this one exponential minus will become exponential plus Ia over h cross p. Actually, plus Ia over h cross p is nothing but A dagger. When A inverse is equal to A dagger, then it is naturally is a unitary operator. So unitary operator, the speciality of unitary operator is it preserve the norms, which we are going to see in future lectures. And here the inversion operation is shifting something right to left. This inversion operation shift something here in this case is position to the right or left. We will see further. Now let us see how operators transform. Let us say we have an operator Q which acts on the new wave function with the new coordinate system psi prime. Then we have another operator Q prime uh, which act on the old coordinate system. Psi is a wave function in the old coordinate system. Now, uh, this can be implemented by this. That is, uh, when when T dagger act on psi, because this translational operator is also Hermitian operator. So, psi T dagger gives you the uh, T dagger psi will give you the psi prime, and similarly the get uh, t which act on the get psi will give you the get psi prime. So which is equal to here psi psi q prime get psi. So that's what I have written. If we compare right hand side and left hand side, uh, T dagger Q T is equal to Q prime. So that's what I have written. Q prime is equal to T dagger Q T. This is the translational operator. As I said, translational operator is an unitary operator. It will preserve the norms. It will not change the physics behind this system. So now we can see the translational symmetry. Let H prime, like here H prime, instead of Q prime, you take H prime, which is equal to T dagger H T. So, which will give you, since this unitary operator preserve the norms, this T dagger H cat T cat is equal to H cat, because it preserves the norms. That means we know that T dagger T dagger is equal to H cat. Now, take this equation, take this expression. Here I have taken this, and you multiply both sides by t. This equation I am multiplying by t. So t dagger h t, which is equal to here right hand side also I am multiplying with t. Since it's a unitary operator, this is equal to 1 unitary unit operator 1. So since it's a unitary, so that means h cat t cat is equal to t cat h cat, or h cat t cat minus t uh, h cat is equal to 0. That means h will commute with t. This is equal to commutation of h with t, which is equal to 0. That is, the system has a translational symmetry. It will not change, the system will not change uh, by the translational operator. That is the meaning of this commutation. This commutation shows that the system has translational symmetry. One of the application of a translational operator is Bloch theorem. The Bloch theorem states that the solution to the Schrodinger equation in a periodic potential can be expressed in plane waves modulated by a periodic function. We are going to see the proof of this. This is valid when psi of x is non-degenerate. That is, when there is no other wave function with the same energy or and wave number as psi of x. So we consider a periodic system. The atoms are arranged in a periodic way to the infinite distance. Say the lattice constant between two atoms is A is same. So it will keep on continuing this from positive direction as well as negative direction. So this A is fixed. So The wave due to the symmetry, the potential will be the same. So psi x plus n indicate number, and A is the distance between two atoms. Psi x n of A is equal to psi of x because it's a symmetrical one. So the wave function will be same in every case, irrespective of the which atom you are selecting, because it has periodicity. The potential energy is periodic in a period A. That is very important. Now consider the wave function psi, which is a function of x plus A. You will get same by using the translational operator t. When t act on psi of x, you will get psi x plus A. We will go in detail further. When translational operator act on the wave function psi of x, we will get the eigenvalue lambda multiplied by this wave function psi of x. Since T is the unitary operator, and the unitary operator means it will not change the norms. That means lambda must be equal to 1. That is, lambda will be in the form of e power minus e power I pi, where pi is some real constant. By convention, pi can be written as q minus q a, where H cross Q is called crystal momentum, because we are dealing with the periodic crystal. So psi of x minus a is equal to e power minus iqa. This is the translational operator. This exponential we have seen in the beginning of our class. So except there we got q is except this H cross q is crystal momentum. So which is multiplied by psi of x. The above equation can be written as more conventionally that psi of x is equal to e power not minus e power plus iq u x, where ux is the periodic function of x. So there is a periodic variation. So u of x plus a is equal to u of x, because you have periodicity in the crystal system. So here eiqx is the traveling wave. Remember that traveling wave. So what we have seen at the beginning, the Bloch's theorem says that the stationary state of the particle in the periodic potential are periodic functions multiplying the traveling wave. Traveling wave, that is periodic function multiplying the traveling wave. This is nothing but your traveling wave. So in quantum mechanics, we used to say e power ikx is a traveling wave. Here is a crystal system. So as I said, this is H cross q is the crystal momentum. So this is about the Planck's theorem. We have seen the proof also. It's not a tedious proof. It's just a very simple proof we have seen. So thank you very much for watching my video and supporting me continuously. Thank you very much.